Welcome to The Explainer. So, picture this, stepping into a reality that feels pulled straight out of a Blade Runner matrix. A world where edge robotics aren't just running rigid code, but natively processing their environment with this incredibly fluid, breathing biological grace. For years, we've been trying to jam these massive, bloated, classical AI models into the brains of physical machines, and honestly, it simply isn't working. It's a dead end. Today, we're tearing down that entire paradigm. We're going to explore exactly how we are replacing those inefficient black boxes with ultra-efficient brain-like architectures. Our core focus for this explainer is a truly profound breakthrough: natively continuous neurobiological hybridization. We'll be breaking down how synthesizing spectral CAN topology with baby dragon hatchling, or BDH, architectures is finally unlocking true edge-native autonomous systems. Okay, let's dive right in. Here is our system boot sequence for today. 1. The black box bottleneck. 2. Spectral topology and CANs. 3. The baby dragon hatchling. 4. Bridging mind and machine. And finally, 5. Edge-native geometric homeostasis. All right, starting with number 1, the black box bottleneck and the limits of our current architecture. To really grasp why we need a new approach, we have to look at the massive friction between our current AI and physical reality. Think about classical LLMs and transformers. Sure, they're incredibly powerful, but under the hood, they are messy. They're completely cloud-dependent. They suffer from rigid KV cache memory bloat, which is essentially their short-term memory just filling up until the system crashes, and the processing itself is an uninterpretable black box. Now contrast that with embodied robotics. If you want to drop an autonomous agent into the physical world, running on an edge device like, say, the NVIDIA Jetson Orin Nano, you are immediately hit with strict metabolic limits. You absolutely need continuous localized learning, and you need zero latency. Taking continuous physical reality and chopping it up into discrete text tokens for a transformer to read, it's lossy, it's agonizingly slow, and it is computationally disastrous for an edge device. The machine literally can't think fast enough to survive. Moving on to part 2, spectral topology and CAN-ins, which serves as the System 1 physical substrate. This is where the geometric elegance really shines. It's all about this topological inversion. In a standard classical neural network, your nonlinear activation functions are locked away inside the nodes themselves, right? Just tangled up with all these static weight matrices. But with the Kolmogorov-Arnold network, or CAN architecture, we do something wild. We literally rip the nonlinearities out of the nodes and relocate them onto the edges. These edges suddenly become dynamic, breathing topological B-splines. And the nodes? Well, they're completely freed up to perform pure holonic summation. They just act as simple, pristine aggregators. It's a fundamental rewiring of how a machine processes sensory data from the ground up. And the immediate real-world benefit of this rewiring? Safety. Absolutely crucial when we're talking about physical robots. We finally get white box interpretability. Because those nonlinearities are now localized entirely on the edges as 1D B-splines, the system's logic is no longer trapped in some mysterious black box. The precision of any belief update becomes mathematically explicit. A human engineer can directly plot the spline to audit exactly how the system weights its prediction errors. We are literally seeing the mathematical geometry of the machine's trust. No more guessing. But wait, it gets better. We don't just map a single signal onto these edges. We use a universal signal decomposition framework to map 3. In classical setups, if you want to route different types of data, you have to build parallel neural pathways that eventually get totally out of sync. Not here. A single KAN edge handles multiple frequencies in pristine mathematical superposition. They exist simultaneously on the exact same edge without interfering with each other. It's incredibly efficient. So what are these frequencies doing? Let's connect this back to our biological metaphor. Think about how your own brain handles the world. First, you have the gamma frequency running at 30 to 100 hertz. That handles your fast sensory reflexes, like the immediate error correction when you trip over a curb. Then you've got the beta frequency handling mid-level spatial routing and memory. And finally, the alpha frequency. That represents your slow, foundational structural context, the basic, unshakable reality of your environment. This system neatly separates those rapid physical reflexes from the long-term stable realities, and it updates all of them dynamically, on the fly. Which brings us to number 3, the baby dragon hatchling, acting as the higher-level System 2 mind. To really wrap our heads around the BDH, we need to demystify this concept of monosemantic sparse activation. Now, unlike a dense transformer, where millions of parameters fire all at once, creating a massive and tangled energy drain, the BDH actually works a lot more like our prefrontal cortex. It enforces extreme biological sparsity. At any given time, only the top 3 to 5% of neurons are firing. And because of this forced sparsity, every single neuron ends up representing a distinct, unentangled concept. It only lights up the exact neural pathways needed to solve the specific problem in front of it. That saves massive amounts of compute. And here is the total game changer for that memory bottleneck we talked about: Hebbian working memory. Instead of hoarding past context in a rigid KV cache matrix that just linearly grows until the hardware throws a fit and crashes, this biological graph embeds its working memory directly into its synaptic weights. It uses rapid plasticity to adjust on the fly. It is literally rewiring its own physical connections in real time. This brilliant mechanism permanently replaces that bloated KV cache, giving the agent effectively infinite context length without ever maxing out its memory bandwidth. Section 4. Bridging Mind and Machine. The continuous logic loop. Let's ground this with a real-world scenario. Imagine our autonomous agent is walking and encounters an anomaly, like a super slippery floor it can't quite navigate. Step 1. The KN's physical reflexes hit a high urgency state because those fast gamma splines can't resolve the slip. Step 2. This unresolved physical error vector is instantly fired straight up into the BDH mind. The sparse graph lights up, crunching the spatial logic. Step 3. The moment the BDH solves it, it immediately injects that solution right back down as an alpha prior. Notice what's missing here. There is no LLM pausing to type out its thoughts token by token. The latent space graph traversal of the BDH maps perfectly and directly into the KN's topological math. And mapping this entire synthesis out reveals this beautifully unified life cycle. We see the whole continuous loop: detection of the slip, expansion of the error, escalation up to the BDH oracle, grounding of the new logic, and finally, compilation. When that top-down logic from the BDH cascades back, it mathematically shifts the foundational alpha curve of the con substrate. The local gamma frequencies immediately start shaping their high-frequency splines around this newly updated logical foundation. The system snaps back to stability, the robot catches its balance, it achieves what we call geometric homeostasis. I want to highlight a quote from the source material that really hits the nail on the head. We collapse the divide between semantic logic and physical reality. We should probably just pause for a second to reflect on how huge that is. The machine is no longer awkwardly translating physical reality into clumsy discrete text tokens for a language model to read. It's a natively continuous flow. The semantic logic literally becomes the physical geometry of the machine's reflexes. Which takes us to our final phase, number 5. Edge-native geometric homeostasis, the autonomous future. So what does all this actually mean for us? Well, it means we are unlocking a literal cyberpunk reality today. First, because we bypass language entirely, we get zero chain of thought latency and zero risk of linguistic hallucinations randomly telling a robot arm to do something dangerous. Second, because of the hypersparsity, the KAN pruning its splines and the BDH only firing 3% of its neurons, we achieve absolute metabolic viability. We can run a billion-parameter hyperintelligent cognitive agent purely on local robotics without melting the hardware. And third, as we discussed, we maintain pure, auditable white box safety from top to bottom. We are talking about sleek, self-contained robotic entities. This is the culmination of everything we've explored in this explainer. This isn't just a machine running lines of rigid, precompiled code. It is a natively continuous neurobiological hybrid. It's an agent that breathes, that structurally adapts its own internal geometry on the fly, and minimizes its variational free energy entirely on the edge. No cloud connection in sight. We have definitively moved beyond brute force scale, and we are finally moving beyond the black box. All of this leaves us with a pretty profound, maybe even a little haunting, realization about the trajectory of artificial general intelligence. You know, we've spent years teaching machines to talk to us, just so we could try to understand their intelligence. But now, we've given them a native, continuous architecture where they literally no longer need our words to understand the physical world. So the question you should take away from this explainer today is this: when the machine no longer needs language to think, what will it build next?